Virtual Algebra 2, we're starting a unit on probability. As I think I've mentioned before, probability tends to be one of those things that just some people get it and some people don't right away. And those of us who don't, me included, have to work particularly hard at making sense out of all of this. And I've found through the years that for some reason, students that normally do really well with math don't like probability very much and struggle. Like me, like I said, and students that normally struggle with math tend to love probability. It tends to make a sort of common sense to them that it doesn't to people like me. Anyway, we'll see how that goes. We're going to be learning about a lot of different tools and equations, and one of the hardest things is going to be to figure out in which situations to use each of the tools. So I'm going to try to focus on that as we move through all of this stuff that we're going to learn. Alright, so if you've been with me this year, then you've heard me talk about how probability equals happy over total. I should be more specific about what I mean by that. There's some words that are used, some vocabulary in probability that's going to be important for us. One word is an event. And what we mean by an event when we're talking about probability is a particular result or an outcome in a given situation. And a sample space is the set of all possible outcomes or results. So for example, if I have a drawer full of socks, say I've got equal numbers of white, black, blue, and green socks. Say I've got 8 of each, so that's 32 socks in total. Those 32 socks, that's my sample space if I'm going to pick a sock out of the drawer. And if I'm looking to find out the probability of getting a green sock, then the event is going to be the 8 green socks that are in the drawer. So, if I have these 32 socks and 8 of them are green and the others aren't, well, it's not too hard to figure out the probability. But just to make the point, the event is the 8 green socks. The event is I get a green sock, right? And there are 8 ways that I could get a green sock because there are 8 green socks. And the sample space is the 32 socks that are in the drawer altogether. And so there are 32 outcomes in the sample space. And so when I say that the probability of an event is happy over total, what I mean is really that the probability of an event is the number of outcomes in the event divided by the number of outcomes in the sample space. So in this case, 8 ways to get a green sock because there are 8 green socks, and 32 ways to get a sock at all because there are 32 socks. So the probability is 8 over 32 or 1 over 4. Okay, does that make sense? So that's a simple example. It's probably time to move on to some more interesting ones. That is what's known as a theoretical probability, meaning we didn't actually do any pulling out socks from a drawer. We just thought about it and said, look, if each sock is equally likely to get, which may or may not be true, then 8 out of 32, I should get a green sock 1 out of every 4 times, or 25% of the time. There's also something called an experimental probability, and that's a little bit different. To find an experimental probability, I have to do an experiment. And in probability math, an experiment is a series of trials. A trial is one given chance to see whether or not an event happens or what the outcome of an event is. So for example, I could, close my eyes, turn off the lights, and pull a sock out of the drawer. Maybe I get a green sock on trial 1, and then trial 2 I get a white sock, and then green, blue, black, and black. So maybe I do 6 trials in my experiment. Well, from this, the probability of getting a green sock, well, I got 2 green socks out of 6 tries, so it's 2 out of 6 or 1 over 3. Whereas the probability of getting a white sock was only 1 out of 6, a blue was also 1 out of 6, and a black was also 2 out of 6 or 1 out of 3. Notice that all the probabilities add up to 1. That's not a coincidence. That should always happen, and that means that the chances of something happening are 100%. Because, of course, something is always going to happen. Alright, so there's a difference between theoretical and experimental probability. Our theoretical probability for getting a green sock was 1 out of 4. And our experimental probability turned out to be 1 out of 3. They're not the same, and they're never going to be exactly the same. If we've calculated our theoretical probability correctly and included all aspects of the problem, then the more trials we do in our experiment, the closer our experimental probability should be to our theoretical probability. If it turns out that our experimental probability is way different even after many, many trials, then we've probably messed something up in our theoretical probability calculation, right? Maybe there are some red socks in the drawer and we forgot about that, or maybe there are more than 8 green socks. Okay, so that kind of mistake could affect your theoretical probability. All right, so that's one situation we've talked about for probability. And here's another one. If you look in your book on page 629 at example 1, well, first of all, you can tell that this is definitely an old book. It looks like it's published in 2003. They're talking about floppy disks, which most people don't even know what they are anymore, but it used to be a way to store information for a computer. Anyway, so suppose we have the kinds of disks that they're talking about there in that problem, and they want to know what's the chances that we randomly pick out a red disk if we just grab one of them. Okay, we're not going to look. We're going to close our eyes or whatever. It's going to be random. But all we have to do is think about happy over total. The number of ways that we can get happy, meaning get a red disk in this case, and the number of things that can happen. Well, there are 9 disks, and 2 of them are red. So 2 out of 9, which is roughly 22%. 2 over 9 is an exact answer. 22% is approximately correct. All right. Was that a theoretical or an experimental probability that we just figured out? Right, it would have to be theoretical. We didn't actually go and try this, grabbing disks and trying again and again. So it was a theoretical probability. And most of the ones we're going to calculate until the very end of this unit are going to be theoretical probabilities. All right, so now we're going to move on to something a little bit different called geometric probability. So sometimes the situation has so many possible outcomes that the approach we've just talked about is not actually feasible. Here's an example of that. Suppose we have a sandbox, a box of sand, kids play in it, and it's 2 meters by 2 meters square. And we just randomly drop a marble somewhere in it. So we have no idea where it's going to land, but except that it's going to land somewhere in the sandbox. Now there are basically an infinite number of places where this thing could land, and so trying to count up the number of outcomes in the sample space is going to be a daunting task. But what we can do is, if we want to know, for example, what's the probability that a marble lands in the top right quadrant of this box, that is in the dashed box you see in the top right corner, we can use area to take the place of counting up the number of outcomes, because the number of outcomes should be proportional to the area of a given part of the box. So if we want to know the probability that the marble lands in the top right quadrant, we can compute the area of that, which is just 1, and the area of the whole thing, which is 4. And so in a way we're still doing happy over total, the area of the event, sounds kind of funny, and dividing by the area of the sample space, or the area of the entire possible region. So in this case, 1 over 4, 25%. And again, this is called geometric probability. Your book gives us another good example of this. Example 2, basically a really, really bad darts player. This person is so bad that all we can do is guarantee that they'll hit the board. But other than that, where the dart lands is completely random. That's kind of like the way I play darts. So they want to know what the probability is that this person lands their dart in the outer ring. Okay, well, we need to find the area of that event, which is going to be the area of the whole circle minus everything inside the outer ring. So pi times 3 squared minus pi times 2 squared. So we're finding the area of that ring. That turns out to be 5 pi, as you can see here. And then the area of the sample space, the total area. And that's just 9 pi. And we divide those two, the pi's cancel, and we're left with about 56% chance.